Hello again, this is Mark Summers from Summers Technical Services. We're going to revisit our V-block assembly model from the other day. We're going to do a couple of things. One, we're going to look at how to fix our interference problem between the U-clamp and the V-block that I discovered after we finished the assignment up. And then we're going to do a finite element analysis on that U-bolt or the U-clamp to see how much force it's going to take if we wanted to leave the V-block like it is and just try to pull the tongs out on that thing and get it to slide over and eliminate that interference. So we're going to put a load at the bottom representing that pull force and get an idea how much that thing deflects, see if we could pull a little bit and get it to spring out and slide over. So it'll give us some insight into that. And it'll give us a chance to learn a little bit about material properties and stress analysis and failure modes. So let's get started. So let's pull up just the part model, and so we can do an analysis. It'll just be a part model analysis. So the way we do that is we run the Solidworks Simulation module, and it's just another tab on the tab list up here. And if it's not showing up on your tab, just right click and you can turn these on and off. There's lots of different tabs we can turn on and off, and one of them is a simulation tab. So mine's turned on, and you want to make sure you've got the material defined in your model, and everyone will have a different unique material. And mine is 6061 T6 aluminum. And when you apply this material, we're going to need to extract some of these mechanical properties from the database here that comes with SolidWorks. We need to know, well, first thing we need to do is make sure you're on the inch, pound, second units. I think it defaults to metric units since the model's in inch units, we want inch, pound, second units. And down here, you're going to read off these values. You're going to get a value for elastic modulus along with the units. You're going to get a value for the tensile strength, or the ultimate strength sometimes it's called, also with units. And we need to know the yield strength. We need to know those three parameters. So take note of those, apply and close, and now my material is assigned in the model. And let's start this new study. So I'm going to use this pull down, create a new study, and there's lots of different types of studies. We can do buckling, nonlinear. We can actually even do drop test if we wanted to. So we're going to use just a regular static simulation. We'll give it a name if we want to, but if not, we'll just use the default. And it creates a new tab down there at the bottom with this information. We can have multiple analysis run on the same part model, and this is all contained in this part model, so this is a nice thing. All right, so now we got another set of buttons up here, and we pretty much just answer questions moving left to right and then run the analysis. So first thing we'll do is apply the material. Even though we applied the material in the model, we need in the model feature manager, we need to apply it in the simulation manager. And since it's already chosen a 661, it assumes that's what I want. And it gives you indication down here. These red values are values that it has to have in order to run. The blue are nice to haves, and the blacks are optional. So I'll just hit apply close. So now that material information has been applied in the simulation module, and we'll go to the next button, which is fixtures. And fixtures are another word for constraints. And so we need to tell this model where we're going to hold on to it, and we're just going to hold on to it at the top here, because the bottom is going to be free to rotate or free to move. And so we'll go to fixed geometry and just grab this top face and say OK. It gives us a nice little indicator. The arrows are pointing in all three directions, which means that top surface cannot move in the X or the Y or the Z direction. And these X, Y, Z directions are defined by the triad in the model that you're already familiar with. Once I do that, I get a new entry down here in my simulation manager, and there it is right here, fixed geometry right here. So that's the one I just added. So now let's put the load on there. We're going to put a load on this face and this face, and we're going to push out both directions evenly, and everyone will have a different amount of force to put on there. In my case, it's going to be 200 pounds. The value I give you is the total load. So for my case, it's 200 pounds, which means I'm pushing 100 pounds on this face and 100 pounds on the other face. So I'm going to go to external loads, pull this down, lots of different load types, gravity loads, pressure loads, torque and forces. I want a force load, and it's just got a blue box. I can toggle between force and torque. I want force. It's got a face there. I can select that face, and it gives me a nice little indicator. I can select this face over here, and it assumes I want to go normal to that face, which is exactly what I want. I want to go normal both ways. I need to switch this to total load, because I want to put the total load here. So I want 100 going to the left, 100 going right. This is popping up as newtons, so I need to do a little Google search and find out how many pounds are in a newton. And that's easy to do with the Googles. So I got a total of 200, so I want to type in my total load in newtons. And you'll do the same with your value I give you in class. And then we'll say OK. So I've got the material defined, I've got the load defined, I've got the constraints defined, and so now I'm ready to create my mesh. Use the run this study, pull this down and say create mesh. You can have different sizes of mesh. These meshes are tetrahedron geometric shapes, and you'll see what they look like in a minute. And we need to do a whole new video about doing meshing. But in general, they're tetrahedrons. You can slide this slider back and forth. If you want a coarse mesh, the tetrahedron is going to be bigger. There's less of them, and you're going to get a less accurate answer, but it's going to run faster. And on the other hand, you can slide it all the way to the right and get a fine mesh, which means small tetrahedrons, lots of them, and a better answer, but it's going to take longer to run. So first time I usually run it at the default. I'll get an answer. I'll run it again with all the same settings at a higher mesh setting. And if the answers don't change, then I know it's converged at that mesh size. So we'll say, OK, let's mesh it. And it spins for a minute or two, or I guess a second or two. And it makes the mesh. And so that doesn't look horrible. I got 1, 2, 3, 4, 5. I got a half a dozen or 8 elements across this thing. And so that's generally enough elements to give me a pretty good answer. So I think I'm satisfied with the mesh for now. And then before I run it, I'm going to save it in case it crashes. And now I'm ready to run it. So I just hit run this study. And we're off to the races. I can get more. Oop, went so fast we couldn't see anything. All right, so I got a pretty speedy computer evidently. Now we've got results down here, and we're gonna ask for different results depending on what we want. It gives us the von Mises stress, and this is important for failure criteria for ductile materials like aluminum, which is what we're using. And the failure criteria says that if the von Mises stress in your part gets greater than the yield strength of the material, then it's going to fail. And so that's a pretty good criteria. And so I can just monitor the von Mises stress and compare it against my ultimate strength and the yield strength, and I can determine if it's going to fail or not. All right, so here is, so I got those answers. We'll check those later. I want a displacement value. I want to see how far these things move out. And so I have to ask for a particular type of result. It gave me these by default, but I'm going to ask for another one. I want to right-click on the results and say I can define a stress plot. I can define a factor of safety plot, which we'll do in a minute. But now I want to define a displacement plot. Displacement, deflection, same thing. So I want to ask for the deflection in this direction, which in my case is the z direction. So I'll ask for that, and I want to get it in inches. And say OK. And this gives me this radically over exaggerated deflection. It's really not going to deflect that much. And you can see up here it's 4 times almost the scale of the real deflection. And if you don't like that, you can turn it off. I want to turn off deformed result. And it gives me this nice contour. So blue is large negative displacement, which is over here. It's moving this way. The red is large positive displacement. It's going the other way. And it makes sense that those numbers are the same. Their absolute value is the same. And it makes sense that the green is right here in the middle where it transitions from positive to negative. So this thing is making sense. If I'm still not sure if it's making sense, I can right click on it and I can say animate, and it gives me a nice little picture. And if I would have turned on deformed result and then do an animation, it gives me a nice little visualization. It's, yeah, that makes sense. It's going to go out, it's going to come back. And so this is all making sense to me. All right, so I want to write these numbers down, to get these displacements. I want you to write your numbers down. And this is exponential notation, so it's 7.427, 10 to the minus 2. So figure that out and write that down. And the units also, this is in inches. And I also want you to find the displacement right here on this vertical wall where this thing transitions to this corner here, because I want to know how far it moves out there, because that's about the spot where the end of that V-block, the V-block ends. So right that transition right there, let's get a displacement. I could look at the color and kind of guesstimate, but there's a nice little probe up here under Plot Tools Probe, and you can probe on the model and get a particular displacement or any parameter at a particular node. And so this is node number 9547, and this is the XYZ location of that node. And there's the value of this displacement. So it's moving 2.464 times 10 to the minus 2 inches. And so I want you to write that number down as well, so we know how much is displaced there. All right, so then now let's go back to the von Mises stress. I'm going to double click it to activate the von Mises stress. And you'll notice that the yield strength of the material is pretty much the same value at, this von Mises is no good. I need different units. I got it in metric units. So I want to right click, edit definition, change this to PSI so it matches my other parameters I wrote down. There we go. All right, so these are my stresses. Now I'm a little worried about the mesh, and so I'm just going to go crank up the mesh. I'm going to go rerun. Or no, create mesh. It's going to disallow my analysis I just did, which is okay. I'm going to crank this all the way over and say okay and let it do the mesh again. Should be a lot finer mesh. And boom, it is. It's more elements. That's good. And so let's see if it makes a difference with our values. And so I'm going to run the study again. So it's going to give me better answers, potentially a lot better, and maybe not so much better. And look at this, I've got 336,000 degrees of freedom in about 80,000 nodes, it looked like. All right, so the stresses were pretty close. Let's look at the displacements. They seem pretty close, so maybe it wasn't that much better. But anyway, I can't remember what the other numbers were. Maybe they were close, maybe they weren't. You're going to want to make sure you write your numbers down so you can compare the two. All right, so again, do your plot tools to probe right there at that corner. And there's a new value there. All right, so that's as far as we'll go. Just a kind of an introductory lesson in SolidWorks Simulation. So the last thing we'll do is a factor of safety plot. So I'm going to right click up here, factor of safety plot. Factor of safety compares, so really the best way to look at stress and how it affects your part. Factor of safety compares what the part can handle stress-wise divided by what the real stress is. So big factors of safety means you've got a lot of margin of safety. You've got a lot of room for higher loads before it fails. It's what it can handle divided by what it sees. So what it can handle, there's two things we got to look at. We got to look at factor of safety based on ultimate strength, and we want factor of safety based on yield strength. And so if you take the ultimate tensile strength divided by the real stress right here that we just calculated, ultimate tensile strength divided by that real stress, that's going to give me the factor of safety based on ultimate strength. If you take the yield strength of the material and divide by the real stress, that'll give you the factor of safety based on yield. And what we want for our design to meet code, we don't want to have a factor of safety of 1, because that means it just barely doesn't fail, which is not very appealing to me. So the criteria we're going to use in this class is I want a minimum factor of safety of 2 on yield and a minimum factor of safety of 3 on ultimate strength. If it meets that criteria, then it meets the code, it meets the specifications, and we'll move on. So I want you to calculate all those values during class today. So you'll be running this little analysis. I'll supply you the model, and then we'll compare answers. Everybody is going to have a little bit different material, and we'll compare those at the end of the class, get an idea of which material might work or not. So that's it for now. Again, this is Mark Summers from Summers Technical Services. Hit the subscribe button and hit the notification bell so you get notified of this and other future videos. So thanks for watching.